Friends, welcome back to Edupedia World. Today we will discuss about another kind of machine which is called a pulley. The discussion will be focused on the basic definition of pulley, and then we will see two types of single pulleys. That is, one is single fixed pulley and the other is single movable pulley. So let us get started with today's lecture. A pulley is defined as a device which is disc in shape. So a pulley is a disc with a groove around its rim. Disc with grooved rim and a rope or a string goes around the rim, around which a rope goes, and the disc is free to rotate about an axis, and this disc rotates about an axis. Now a pulley system can have multiple pulleys, so there is the possibility of having multiple discs with grooved rims, and the whole package can be termed as a block and tackle, the multiple disc with ropes around it. We'll see how that works, but to begin with, let us see the very preliminary kind of pulley system in which we have a single pulley. So for a single pulley system we have two subcategories. One is called single fixed pulley, and the other is called single movable pulley. So what is the difference between single fixed pulley and single movable pulley? The fundamental difference between the two is that in single fixed pulley the axis of rotation is fixed in a position. So for this, axis of rotation is fixed at a position, and single movable pulley, the axis of rotation is not fixed, that is, it is movable. Now let us see with the example of a figure what does this imply. I will begin with single fixed pulley. So the single fixed pulley, the concept is that you have a rigid support here, and through this rigid support hangs a pulley, that is the disc, via a rod, and this position, the center, is the axis. So this disc rotates about this fixed point, this axis, and since this axis is fixed, as it is directly attached to the rigid support, this pulley is an example of single fixed pulley. Now what does this do? What this does is that it changes the direction of force. What do I mean? Now this is a pulley, and about the rim there is this rope, which for the calculation purposes we will assume to be having zero mass. Now suppose this is a load, let's say this is a load L, and imagine you want to take some water out of a well. It would be rather inconvenient to pull the rope upwards. Suppose there were no pulley, then you had to pull it upward this way, which is not comfortable, but it is much more comfortable to pull the rope downwards because you can use your own way to pull it downward. That is exactly what this pulley, the single fixed pulley, helps us do. So this is the load, and here we apply the effort. What happens is that this load creates a tension here, and it also, this tension, since this is a massless rope, the tension will be uniform throughout the rope. So this tension is transferred over here too, and if we equate the forces, what we will see is that the effort which we are applying is equal to the tension, and this tension is balancing the load. So the tension is also equal to the load. As a result, the effort and the load are equal using these two equations. So what is happening is just that the direction of the applied force is changing. There is no gain or loss of effort. Now if we see the definition of mechanical advantage we know is load by effort. So for this case, since effort and load are same, mechanical advantage turns out to be 1 or 100%. So for a single fixed pulley, the mechanical advantage is 1. Now what will be the velocity ratio? Velocity ratio is defined as the distance moved by effort upon the distance moved by load. So let us imagine that the effort moves at a certain distance, say dE. Now this is the distance moved by effort, then the whole rope goes down by dE in this section. As a result, the whole rope goes up by dE in this section, and the load ultimately moves upward by the same distance dE. This dL is equal to dE. Now we know that the velocity ratio is the distance moved by the effort upon the distance moved by the load, and since the distance moved by the effort and distance moved by the load is same, we can replace dE by dL, and that gives us a velocity ratio of 1. Now we know that the mechanical advantage is 1. We also see that the velocity ratio for a single fixed pulley turns out to be 1. And what does this mean? This means that there is no gain in speed and there is no gain in effort. So the only thing that the single fixed pulley is doing is that it is changing the direction of the load, which is actually advantageous to us in scenarios like pulling out a bucket of water from the well. And we can also calculate the efficiency using these two. What is efficiency? We know that the efficiency is mechanical advantage upon velocity ratio, and since both of them are 100% or 1, the efficiency turns out to be 1, which is equal to 100% in terms of percentage, or in terms of fraction it is 1, that is 100% efficiency. Now this is the ideal scenario, that is efficiency is 100%. But in practical day-to-day scenario, the efficiency is not 100%. Why so? Because there are losses based on friction, there are frictional losses. There is a mass of the rope which we actually consider to be 0, and there are other losses which are not taken into account. So if we take those things into account, the efficiency will come down below 100%. But what will be the influence of such frictional and other losses on mechanical advantage and velocity ratio? The velocity ratio will not change, it will be 1. Why so? Because velocity ratio is the proportion of distance moved by effort to distance moved by load, which is always equal to 1:1. Whatever be the frictional losses, the distance moved by effort and distance moved by load are same, so velocity ratio does not change. What changes is the mechanical advantage. Since there will be losses, we'll be requiring to apply more effort to lift a certain load. As a result, the mechanical advantage will become less than 1. And since mechanical advantage would become less than 1, the efficiency would also become less than 1. So this gives us an idea about the single fixed pulley concept. Now let us see what a single movable pulley concept is. The basic difference between single fixed and single movable pulley can be seen through this diagram. What happens is, in single fixed pulley, the pulley is directly attached with the rigid support, but in single movable pulley, what happens is there is a support over here, but that support supports the rope rather than the pulley. And pardon my non-circular pulley, this needs to be a circular disc, but for representative purpose I suppose this should suffice. Now what is happening here is that this rope is tied directly to the support at the top, so this point does not move. Now the load is supported from the center of the pulley. This is the axis, this is where the load is present, so this is my load, and here is where I am applying my effort. So here is the effort. Now since the effort is applied here to balance the load, there will be a tension created here. Let me do it with a different color. There will be tension in the opposite direction here, and as we saw in the previous case, the tension will be uniform throughout the rope. So rather, the tension will be in upward direction towards the effort. So when the tension is here, there will be another tension component here with the same magnitude T, capital T. Now what do we see here is that this pulley, when we apply effort and try to move it upward, the pulley moves upward. So the pulley is not fixed. This is an example of single movable pulley. Now what will be the distance, relative distances moved? Suppose that I move this position by a distance dE. So I moved this by dE. As a result, what will happen is that since the rope has two components, this part and this part, moving the rope by dE will move the load by just dE upon 2. Why so? Because this whole dE is distributed into two segments, and each segment is equivalent of the load being moved. So basically the distance moved by the load will be half of distance moved by effort. So once we know this, now let us see the force equivalence. What will be the force equivalence? This load, effort and tension are equal, so E is equal to T, since that is what we see here, and this load is balanced by this and this, so the load is equal to 2T. This load has two tension forces balanced in it, so load is equal to 2T. Now we know that the mechanical advantage is load upon effort. Load upon effort, we just calculated that the load is 2 times tension, and we know that the effort is tension, so this turns out to be 2 or 200%. So the mechanical advantage of a single movable pulley is 2. What does this mean? This means that we require only half the load, rather half the value of load in terms of effort to move the load. So if we have something of a 100 kilogram force here, we need to apply just 50 kilogram force to move this load. Next up, we need to calculate the velocity ratio. What is velocity ratio? We know that it is the distance moved by effort upon the distance moved by load. We know that the distance moved by effort is dE. Let me put it as dE. And we know that the distance moved by load is dE upon 2. So if this 2 I take it upwards, that turns out to be 2. What does this mean? This means that the velocity ratio is 2, and effectively that means that the distance moved by the load will be half the distance moved by the effort. So what we see here is that we are gaining on the force. We need to apply less force to move a certain load, but we are losing on the speed. That is, if we move the effort by 1 meter, we are moving the load effectively by 50 centimeter only. And this ought to be true, because this means that there is a conservation of energy, that is, no additional energy is being generated. Now we can apply the equation for efficiency is mechanical advantage by velocity ratio, which turns out to be 2 upon 2, 100%. So in this ideal scenario also we get a 100% efficiency, which in practical scenarios won't be the case. There will be frictional losses. As a result, the mechanical advantage will be less than 200%. The velocity ratio will remain 2, and the efficiency will be less than 100%. So with this, I will conclude the idea of fixed pulleys, rather of single pulleys, both the fixed kind and the movable kind. We saw that the single fixed pulley is used as just to change direction, whereas the single movable pulley is used as a force multiplier. And it also helps us to lift much larger load than the effort we are applying. Next chapter we will discuss about combinations of pulleys. This discussion was about single pulleys. Next chapter will be combination of pulleys, and once we are done with the combination of pulleys, we will see certain numericals. To conclude this chapter, I will just put additional note that in the single movable pulley, we can again change the direction of the effort applied by adding a single fixed pulley here, so that it is easier to apply the load downwards. Okay, let me conclude the lesson now. We'll discuss the combination of pulleys in the next class. Till then, have a great day.